Hello and welcome to recording number 2 for Wednesday, March 16th. This is going to be the last video for you guys to wrap up Unit 3, Lesson 1. So in the last video, we did an example using common external tangents. For this video, we are going to do an example using common internal tangents. So let's take a look at our diagram and see what we're given. Here we have circle C and circle D. And we have two common internal tangents to each of those circles. We can see we have tangent line BA, and we have tangent line CD. Okay, since both of these segments, CD and AB, are tangent to both circles, at the point of tangency to the radius, they form 90-degree angles. So we really have two right triangles here. And so we want to find the value of x, which is going to be the radius of circle D. And we want to find the distance between the centers of the circle. And so that distance that we want to find is going to be the segment from C to D. So let's look and see how we can do this, knowing that we have two separate right triangles. So the first thing we're going to do is we're going to do a quick proof to show that the two triangles that we see in each of our circles, let me outline those, CEA in red. We're going to do a quick proof showing that triangle CEA is actually similar to, let me get another color here, is actually similar to triangle BED. And so we're going to revisit, if you think back to Geometry A Unit 7, when we worked with similar right triangles. So the first thing we're going to do is we see that segment AC is perpendicular to segment AB. So AC is here, and AB is one of our common internal tangents. And so what that tells us is that the tangent is perpendicular to the radius. We also see that segment BD is perpendicular to segment AB for the same reason. A tangent is perpendicular to a radius. So BD is over here, and it's perpendicular to that same common internal tangent. So because these two pairs of segments are perpendicular, we know that we have our 90-degree angles formed. So I can say that angle from C to A to E, this angle here, angle CAE, must be congruent to angle DBE, because they are both right angles. So they both equal 90 degrees. Or in other words, you could say the right angle congruence theorem. What we also see here is a pair of congruent vertical angles. So CEA is congruent to BED. CEA is congruent to angle BED, and that is by the vertical angles theorem. And so now we've shown two angles in one triangle are congruent to two angles of another, so we are able to state these two triangles are similar. And what that allows us to do is to then write up a proportion comparing the corresponding parts of each of these triangles, and we can then solve for the length from B to D. So now that we see the two triangles are similar, we can set up the following proportion. I can say that, and my congruent statement will help me set this up. I can say that AC is to BD, so AC is to BD. So that's the first and third letter of the first triangle, and the first and third letter of the second triangle. That is to AE over BE. The last two and the last two. So plugging in values for this proportion, AC is 5, BD is X, so 5 over X is equal to AE, which is 8, over BE, which is 12. And remember, when we solve any proportion, we cross multiply. So we do diagonally across the equal sign here. So I go 5 times 12 is equal to 8 times X. 5 times 12 is equal to 8 times X. 5 times 12 is 60. So 60 equals 8X. And to solve for X, which is the length of B to D, I just divide by 8 on both sides. And so that tells me that X is equal to 7.5. Alright, so now I found the value of X. Next I want to find the distance between the centers of the circle. So what I want to do here is I just want to use the Pythagorean theorem twice. And so what I'm going to do, if you guys want to grab a quick screenshot of this slide, I'm going to clear off some of my writing here, so that way I have more room to work with. So if you want to take a quick screenshot of this, and then I'm just going to get rid of some of my writing so I have room to use the Pythagorean theorem. So let's just get rid of some of this. And I'll leave my diagram with the writing on it. So that we can solve each one of our right triangles. And I apologize, there's no fast way for me to erase my writing here. Almost gone. Okay, so at least now we have some room to work with. So remember, my goal is to find the distance between the centers of the circle. So that's going to be segment D to C. And I just need to use the Pythagorean theorem with each one of these triangles. So I know that the first triangle in red, I can solve for. I have this right angle here. So if I pull this out, this is C, A, and E. And CA is 5, and AE is 8, and I want to find this distance here. So I can use the Pythagorean theorem. A and B have to be the legs forming the right angles, and that'll let me find the distance from C to E. So I can say that CA squared plus AE squared is equal to CE squared. Well, CA is 5, so 5 squared, plus AE is 8. 8 squared is equal to CE squared. Well, 5 squared is 25. 8 squared is 64. And those together will give me CE squared. So 25 plus 64 gives me 89. And to figure out just CE, I take the square root of both sides. So the square root of 89 is about 9.43. So let's just save this length here. From here to here is 9.43. And now I want to use the second right triangle. Over here to solve for ED. So if I just sketch this out, I have B, E, D. BD is 7.5, BE is 12, and I want to find this length here. So my legs are BD and EB. So that's going to be A squared and B squared. So BE squared plus BD. BD squared is equal to ED squared. Well, BE is 12, so 12 squared plus BD is 7.5, so 7.5 squared is equal to ED squared. Well, 12 squared I know is 144. 7.5 squared is 56.25, and that's going to be the length equal to the length of ED squared. So let's add 144 plus 56.25. That gives me 200.25 is equal to ED squared. So I need to take the square root of both sides. And that tells me that ED has a length of about 14.15. So that's this length right here. So if I want to find the distance between the centers, that's going to be C to D, and that equals the two individual lengths, CE plus ED. So CD is equal to 9.43 plus 14.15. Oops. And so the length from C to D is equal to about 23.58. Alright, so now we've seen examples of common internal, common external tangents. We've seen an example using each, and I just have 2 more quick slides of vocabulary to take a look at to wrap up this recording. So here we can see 2 circles are tangent to each other if they have only one common point. So if you look at the diagram on the left, we have 2 tangent circles. We call them tangent because they intersect at only one point here. One point of intersection. Over here, we said 2 circles that have 2 common points of intersection, or 2 common points, are called intersecting circles. So they intersect once, they're tangents. If they intersect twice, they are overlapping or intersecting. And our last slide, 2 circles can be externally tangent if the circles are situated outside of one another. So we call these tangent. More specifically, they are externally tangent. And internally tangent is when one circle sits inside of the other. So they still intersect at one point, but you can see the small circle is located within the bigger circle. So thank you guys for watching. I hope you're having a great week. Those of you who are OGT testing, I hope everything is going well. And remember, my live help session will be this Thursday evening from 6 to 7 p.m.